What if I told you that the world's greatest cities were not designed by different architects, but copied from a single blueprint, so precise, so mathematically perfect, that even today's supercomputers struggle to recreate its geometric harmony? What if the urban planning of Paris, Washington, D.C., St. Petersburg, and dozens of other major cities around the globe were not independent achievements of human ingenuity, but identical reproductions of one master design that appears to have originated from nowhere and everywhere at once? What if every morning commute through perfectly aligned boulevards, every walk past uniformly spaced buildings, every turn through mathematically calculated intersections is evidence of coordination that transcended every known limitation of 19th century civilization? What if the streets beneath our feet carry the signature of intelligence that possessed capabilities we are only beginning to suspect? Tonight, we follow a trail of evidence that leads to an impossible conclusion. Between the years 1850 and 1870, a coordinated global transformation reshaped the world's major cities according to mathematical principles that should not have existed in that era. Principles so advanced, so precisely calculated, that their implementation across continents defies every known limitation of 19th century technology, communication, and coordination. The mathematics carved into these cities whisper of intelligence that operated beyond the boundaries of human capability, intelligence that understood cosmic relationships and planetary mechanics with precision that wouldn't be officially achieved until the space age. The evidence lies not in hidden documents or secret archives, but in the streets beneath our feet, in measurements that repeat with mechanical precision across thousands of miles, as if stamped from the same cosmic template, in geometric patterns that mirror each other so perfectly that chance becomes a mathematical impossibility, patterns that encode relationships between earth and sky, between human movement and celestial mechanics, in a network of urban design so synchronized, so identical in its execution, that it suggests the presence of a singular intelligence operating on a planetary scale, an intelligence that viewed continents as drawing boards and cities as components in a vast geometric equation, an intelligence that left its signature written in stone and steel across the face of the earth, embedded in the very foundations of human civilization, an intelligence that planned not just for the 19th century, but for technological developments that wouldn't emerge for generations, creating urban environments that continue to function with optimal efficiency more than 150 years after their completion. We begin our investigation in the city that should never have existed, a metropolis that emerged from medieval chaos with mathematical perfection that defies historical explanation. Paris, 1853. The gas lamps burn low in Baron Georges Eugène Haussmann's office as he spreads the Emperor's mandate across his mahogany desk, the yellow light flickering across blueprints that seem to glow with otherworldly precision. Napoleon III has ordered the medieval labyrinth of narrow streets transformed into something grander, something more fitting for an empire that stretches across continents, but the documents before Haussmann contain specifications that exceed every known capability of his era. The blueprints show measurements, calculated to tolerances that his instruments cannot achieve, geometric relationships that require mathematical knowledge decades ahead of its time, construction timelines that demand workforce coordination beyond anything previously attempted in human history. Haussmann stares at these plans with growing unease, recognizing that he has become the executor of a vision that transcends his understanding, a vision that treats the ancient city of Paris as raw material to be reshaped according to principles that operate beyond conventional architectural theory. But what emerges from this renovation defies every principle of urban planning known to the 19th century. Haussmann finds himself implementing specifications that appear on his desk without explanation, following construction guidelines that demand precision his instruments cannot achieve, coordinating workforce operations that exceed every documented capability of his era. The renovation proceeds with supernatural efficiency, as if guided by intelligence that possessed complete understanding of complex mathematical relationships, intelligence that could calculate optimal traffic flow patterns decades before the invention of the automobile, intelligence that understood the physics of sound, light, and human psychology with precision that modern urban planners struggle to replicate. What emerges from this renovation is not simply impressive, it is impossible. The new boulevards of Paris stretch in perfect straight lines for kilometers, cutting through the medieval chaos like surgical incisions through living tissue. Their geometric precision, maintained across varying elevations, different soil compositions, and complex underground infrastructure that should have made such accuracy impossible to achieve. Each avenue measures exactly 47.2 meters in width, maintained with tolerances measured in centimeters rather than the meters that 19th century surveying could reasonably accomplish. Not 47, not 48, but 47.2 meters, with a precision that demands explanation, a measurement that appears across multiple continents with mechanical uniformity that suggests coordination by intelligence operating beyond human limitation. In an era when surveyors measured with chains and wooden rods, when calculations were performed by candlelight using primitive mathematics, when communication between cities took weeks or months, this accuracy should have been impossible to achieve, let alone maintain across kilometers of urban construction that required the demolition of thousands of medieval structures, the excavation of millions of tons of earth and stone, and the coordination of workforce operations that exceeded every documented capability of the period. The surveyor's chain of Haussmann's era could achieve accuracy within several meters at best, under perfect conditions, assuming ideal weather, experienced operators, and terrain that allowed for unobstructed measurement. The theodolites available to 19th century engineers might manage precision to within a meter under ideal conditions, but required manual adjustment for every measurement, calculations performed by hand using mathematical principles that were crude approximations of the precise trigonometry required for large-scale urban planning. Yet, the measurements implemented across Paris demand tolerances of centimeters, not meters, precision that requires instruments capable of accounting for thermal expansion, atmospheric pressure variations, gravitational anomalies, and the curvature of the Earth itself. The buildings lining these boulevards stand at uniform heights of 22.5 meters, their facades aligned with tolerances that make 19th century construction techniques appear hopelessly primitive, their proportions calculated according to mathematical principles that incorporate understanding of acoustics, light distribution, crowd psychology, and architectural harmony that wouldn't be formally recognized until the development of modern urban planning theory. Modern laser-guided construction rarely achieves such consistency across such vast distances, even with electronic measurement systems, computer-controlled equipment, and scientific understanding of materials that was unavailable to Haussmann's era. The intersections form geometric angles calculated to optimize traffic flow using mathematical principles that would not be formally recognized by urban planning theory until the 1920s. Angles that require computational analysis of pedestrian movement patterns, vehicle turning radii, psychological factors that influence crowd behavior under stress, and complex mathematical modeling that demands processing power equivalent to modern computer systems. Haussmann's boulevards incorporate these calculations with mathematical perfection, as if their designers possessed computational capabilities that would not exist for another century, capabilities that allowed them to model human behavior, predict traffic patterns, and optimize urban efficiency using principles that modern engineers struggle to replicate even with advanced technology. But here is where the investigation takes its first disturbing turn, a turn that transforms architectural mystery into something far more unsettling. Something that challenges every assumption we hold about the capabilities and limitations of 19th century civilization. A turn that forces us to confront the possibility that human history has been shaped by influences we are not yet prepared to acknowledge. While Haussmann was transforming Paris with these revolutionary measurements, identical specifications were simultaneously appearing in cities across the globe, not similar specifications that might suggest shared cultural influence or gradual diffusion of architectural ideas, but identical measurements, identical geometric relationships, identical mathematical principles implemented with mechanical precision across continents separated by vast oceans and months of difficult travel. Mathematical twins separated by thousands of miles of ocean and continent, connected by coordination that should have been impossible given the technological and communication constraints of the 1850s, connected by intelligence that possessed capabilities far beyond anything officially documented in human history. The synchronicity becomes more disturbing when we examine the specific details of each implementation. Details that reveal not just mathematical similarity, but identical problem-solving approaches, identical construction techniques, identical organizational methods applied to radically different geographic and cultural contexts. In Washington, D.C., Pierre L'Enfant's original plan was being modified to match the exact same 47.2-meter street widths that were simultaneously being implemented in Paris. Modifications that appeared on American drafting tables without documented correspondence with European planners, without recorded consultation with French architects, without any official acknowledgement of international coordination or shared planning initiatives. The American architects produced blueprints that matched Parisian specifications with mathematical precision, incorporating the same geometric relationships, the same proportional calculations, the same optimization principles that were transforming the French capital thousands of miles away. The modifications appeared on American drafting tables with specifications that exceeded every known capability of American surveying and construction technology. Specifications that required mathematical knowledge that hadn't been formally developed in American engineering schools. Specifications that demanded precision that American instruments couldn't achieve. Yet American construction crews began implementing these modifications with efficiency that matched their European counterparts, using techniques that had never been documented in American architectural manuals, following procedures that required skills that hadn't been formally taught in American trade schools. In St. Petersburg, Tsar Alexander II was implementing boulevard systems with identical geometric ratios, identical proportional relationships, identical mathematical principles that were being applied simultaneously in Western Europe and North America. The Russian architects produced blueprints that matched Parisian specifications down to the centimeter, despite the vast differences in climate that demanded completely different construction approaches, terrain that required entirely different foundation techniques, building materials that operated according to different physical properties under extreme temperature variations that ranged from Arctic winters to brief but intense summers. The Russian architects worked with blueprints that incorporated mathematical principles they had never been taught, geometric relationships that weren't part of Russian architectural tradition, construction techniques that required tools and skills that weren't available in Russian markets or training programs. Yet, Russian construction crews implemented these specifications with the same supernatural efficiency observed in Paris, coordinating their work with French and American projects despite communication limitations that should have made such synchronization impossible. In Buenos Aires, urban planners were laying out districts that mirrored the Parisian model down to the degree of angular intersection, implementing geometric relationships that had never been part of Spanish colonial architectural tradition, following specifications that required mathematical knowledge that hadn't been developed in South American engineering schools. The South American architects worked with blueprints that could have been traced from the same master template that was simultaneously being implemented in Paris, St. Petersburg, and Washington, D.C. Yet, no record exists of such templates crossing the Atlantic. No documentation of international architectural collaboration, no evidence of shared planning initiatives that could explain such precise coordination. The Buenos Aires implementation required adaptation to tropical climate conditions, different building materials, different soil compositions, different labor traditions, different cultural aesthetic preferences, yet achieved the same mathematical precision observed in Northern European and North American implementations. South American construction crews followed procedures that had never been documented in regional architectural manuals, used techniques that required skills that hadn't been taught in local trade schools, implemented specifications that demanded precision that local surveying instruments couldn't achieve. The coordination becomes even more mysterious when we examine the specific timing of these implementations. Construction began in Paris, Washington, D.C., St. Petersburg, and Buenos Aires within months of each other, despite communication limitations that should have prevented such synchronization. Materials were ordered using identical specifications before any official correspondence could have traveled between planning offices, suggesting either impossible prescience or coordination by intelligence that operated through means beyond conventional communication methods. Construction crews in different cities encountered identical technical challenges and solved them using identical methods, despite having no documented communication with each other, no shared training programs, no access to technical manuals that described these solutions. When unexpected soil conditions were encountered in Paris, identical solutions were implemented simultaneously in St. Petersburg and Buenos Aires, despite those cities having completely different geological conditions that should have required completely different approaches. When materials proved inadequate in Washington, D.C., identical alternative materials appeared simultaneously in construction sites across three other continents, despite those materials not being locally available and requiring supply chains that hadn't been documented by contemporary trade records. When weather delays affected construction schedules in St. Petersburg, identical schedule modifications were implemented simultaneously in tropical Buenos Aires and temperate Paris, suggesting coordination that operated in real time despite communication technology that required weeks or months for message transmission. The surveyor's instruments from three different continents, despite their different origins, different manufacturing traditions, different calibration methods, all pointed to the same measurements, the same angles, the same impossible precision that exceeded the documented capabilities of period technology. Russian theodolites produced measurements that matched French surveying equipment. American chains yielded distances that corresponded precisely with South American calculations. Despite these instruments having no common source, no shared calibration standards, no documented technical specifications that could explain such uniformity. This synchronicity becomes statistically impossible when we examine the communication limitations of the 1850s, limitations that make the observed coordination appear almost supernatural in its precision and timing. The world of 1850 operated according to the constraints of horse-drawn transportation, sailing ships dependent on seasonal winds, and communication networks that relied on human messengers carrying physical documents across vast distances fraught with danger, delay, and frequent failure. A letter from Paris to St. Petersburg took 3 weeks in ideal conditions, assuming winter storms didn't trap the mail coaches in alpine passes where they might remain buried for months, assuming bandits didn't raid the courier routes that carried valuable correspondence, assuming political upheavals didn't seal international borders and strand diplomatic communications in neutral territories for weeks or months, while governments negotiated safe passage for mail carriers. In reality, correspondence between Paris and St. Petersburg frequently took 6 weeks or longer, with significant percentages of letters lost entirely to weather, theft, or political interference. The route from Paris to St. Petersburg traversed territories controlled by multiple governments, each with different postal agreements, different security concerns, different political relationships that could change without warning, and disrupt mail service for extended periods. Courier routes passed through regions where highway robbery was a constant threat, where winter weather could make travel impossible for months at a time, where political tensions could result in diplomatic correspondence being seized, searched, or destroyed by hostile authorities. Messages to Buenos Aires required 6 weeks by ship, under ideal conditions, assuming favorable winds that could carry sailing vessels across the Atlantic without dangerous storms, assuming safe passage through waters patrolled by pirates and privateers who specialized in capturing merchant vessels that carried valuable cargo, including correspondence, assuming that ships could navigate the treacherous Rio de la Plata Delta without running aground on constantly shifting sandbars that trapped vessels for weeks at a time. The vast South Atlantic swallowed ships without warning, taking their precious cargo of letters and plans to the bottom of the ocean, where they remained lost forever, leaving no trace of the architectural specifications, construction guidelines, or coordination instructions they might have contained. Ships that departed Europe with correspondence for South American architects might disappear entirely, leaving construction projects to proceed without the international guidance that official histories claim guided their implementation. Atlantic shipping in the 1850s operated according to seasonal wind patterns that could delay voyages for months, weather systems that could destroy ships with all hands, navigation techniques that relied on celestial observation and dead reckoning that frequently resulted in vessels becoming lost for weeks while searching for their intended destinations. Communication with South American construction projects operated under conditions of extreme uncertainty, with months-long delays between messages and responses, making real-time coordination impossible, using documented communication methods. Yet, the implementation of these identical urban modifications occurred within months of each other across continents, with construction crews breaking ground simultaneously in cities separated by oceans, with materials being ordered using identical specifications before any official correspondence could have traveled between planning offices, with technical problems being solved using identical methods despite construction crews having no documented communication with each other. Construction schedules were coordinated across continents with precision that demanded real-time communication capabilities. Yet, telegraph networks of the 1850s were regional at best, connecting major cities within individual countries, but lacking the international infrastructure required for intercontinental coordination. The first successful transatlantic telegraph cable wouldn't be laid until 1866, more than a decade after these coordinated modifications began. And even early telegraph systems were unreliable, frequently broken by weather or sabotage, requiring constant maintenance that often resulted in communication blackouts lasting weeks or months. Materials were ordered using identical specifications before any official correspondence could have traveled between planning offices, suggesting either impossible prescience or access to communication technology that operated far beyond the documented capabilities of the 1850s. When specific stone-cutting techniques proved successful in Paris, identical techniques were implemented simultaneously in St. Petersburg, Buenos Aires, and Washington, D.C., despite those cities having no documented correspondence regarding construction methods, no shared technical manuals describing these procedures, no exchange of skilled craftsmen who could have transmitted specialized knowledge across continents. Technical innovations appeared simultaneously across multiple construction sites, innovations that required months or years of development and testing, yet emerged fully formed in different cities at the same time, suggesting either parallel development that defies mathematical probability or coordination by intelligence that possessed communication capabilities beyond anything officially available to 19th century civilization. No international urban planning consortium existed during this period. No global organization with the authority, resources, or communication capabilities required to coordinate simultaneous construction projects across multiple continents. International cooperation during the 1850s was limited to trade agreements, diplomatic treaties, and military alliances that operated on timescales measured in years, not the real-time coordination observed in these architectural implementations. The first global communication cable wouldn't be successfully laid across the Atlantic until 1866, more than a decade after these coordinated modifications began. And even this early cable suffered frequent breaks that disrupted communication for weeks or months at a time. International telegraph networks remained unreliable and limited in scope well into the 1870s, yet the architectural coordination we observe required communication capabilities that exceeded anything officially available until the development of modern electronic communication systems in the 20th century. No global communication network could have coordinated such precise standardization using the technology officially available in the 1850s. No documented communication system could have synchronized construction schedules across continents. No known information transmission method could have distributed architectural specifications with the precision and timing observed in these projects. The mathematical harmony emerging simultaneously across the world suggests a source of knowledge that transcended the technological and organizational capabilities of the era, knowledge that operated according to principles beyond human limitation, knowledge that possessed communication capabilities that history has never officially acknowledged. The coordination observed in these projects demanded not just advanced communication technology, but organizational capabilities that exceeded anything documented in 19th century administration, financial resources that surpassed the documented wealth of entire nations, workforce management systems that could coordinate skilled labor across continents, supply chain logistics that could synchronize material delivery to multiple construction sites separated by vast distances and months of difficult travel. The precision of these measurements reveals itself when we apply modern surveying technology to these 19th century constructions, creating a confrontation between contemporary scientific capability and historical impossibility that challenges every assumption about technological development and human limitation. The results are not merely impressive, they are not simply unexpected. They are impossible by every known standard of historical construction capability, impossible in ways that force us to question the entire framework of our understanding about what was achievable in the 19th century. Modern laser measurement equipment, devices that utilize sophisticated electronic systems, satellite guidance technology, and computational power that exceeded anything available until the late 20th century, confirms that the 47.2-meter standard was maintained across thousands of kilometers with deviations of less than 15 centimeters. 15 centimeters of variation across entire continents, through varying climates that subjected building materials to dramatic temperature changes, over different terrains that ranged from swampland to rocky foundations, despite the use of tools that couldn't achieve such accuracy even on small projects under ideal conditions. This level of precision demands not just advanced planning capabilities, but instrumentation that operated according to principles beyond anything documented in 19th century technology. Instrumentation that could account for thermal expansion of materials across seasonal temperature variations, gravitational anomalies that affect measurement over large distances, atmospheric pressure variations that influence the behavior of measuring instruments, and the curvature of the Earth itself, which becomes a significant factor when maintaining precision over distances measured in kilometers rather than meters. The surveyor's chain of Haussmann's era, heavy links of iron that required teams of men to carry and position, could achieve accuracy within several meters at best, under perfect conditions, assuming experienced operators who had spent years learning to compensate for the inherent limitations of their tools, assuming ideal weather that didn't affect the metal components through thermal expansion, assuming terrain that allowed for unobstructed measurement without obstacles that required complex trigonometric calculations to overcome. In reality, surveying with period equipment involved constant approximation, continuous adjustment for environmental factors that couldn't be precisely calculated, regular recalibration of instruments that drifted from their settings due to temperature changes, mechanical wear, and the limitations of manual adjustment systems that relied on human judgment rather than electronic precision. Surveyors of the 1850s were skilled craftsmen who achieved remarkable results given their limitations, but those limitations were real, documented, and insurmountable using the technology officially available to their era. The theodolites, available to 19th century engineers. Brass instruments that combined telescopic sighting with angular measurement capabilities. Might manage precision to within a meter under ideal conditions, but required manual adjustment for every measurement, calculations performed by hand using mathematical principles that were crude approximations of the precise trigonometry required for large-scale urban planning. These instruments demanded constant recalibration, frequent maintenance, skilled operators who understood their limitations and environmental conditions that rarely existed in real-world construction situations. Yet the measurements implemented across Paris and simultaneously across St. Petersburg, Washington, D.C., and Buenos Aires demand tolerances of centimeters, not meters, precision that requires instruments capable of accounting for factors that weren't officially recognized until the development of modern geodetic surveying. Factors that include the gravitational variations caused by different geological formations, atmospheric refraction that affects the path of light over long distances, the effects of Earth rotation on pendulum-based instruments, and thermal expansion coefficients that weren't accurately calculated until the 20th century. The buildings lining these boulevards stand at uniform heights of 22.5 meters, their facades aligned with tolerances that make 19th century construction techniques appear hopelessly primitive when compared to the precision achieved. Their proportions calculated according to mathematical principles that incorporate understanding of acoustics, light distribution, crowd psychology, and architectural harmony that wouldn't be formally recognized until the development of modern urban planning theory in the early 20th century. These buildings were constructed using stone blocks, cut with precision that rivals modern laser cutting technology, using mortar compositions that demonstrate chemical knowledge decades ahead of their time, using construction techniques that achieved uniformity across vast distances despite being built by different crews using different materials in different climatic conditions. The facade alignment achieves precision that modern laser-guided construction rarely matches, even with electronic measurement systems, computer-controlled equipment, and scientific understanding of materials that was unavailable to Haussmann's era. Modern construction projects that attempt to replicate such precision across similar distances require teams of engineers using satellite-guided surveying equipment, computer-controlled construction machinery, and materials manufactured to tolerances measured in fractions of millimeters. Even with such technology, achieving the uniformity observed in these 19th-century constructions would be considered a remarkable accomplishment, yet these results were somehow achieved using tools and techniques that official history claims were primitive approximations of modern precision. The intersections form geometric angles calculated to optimize traffic flow using mathematical principles that would not be formally recognized by urban planning theory until the 1920s, when computer modeling allowed planners to analyze the complex relationships between intersection geometry, traffic psychology, pedestrian movement patterns, and urban efficiency. These calculations require processing thousands of variables simultaneously, analyzing pedestrian psychology under stress conditions, calculating vehicle turning radii for transportation technology that hadn't been invented, modeling crowd density dynamics that wouldn't be studied scientifically until the development of modern urban sociology. Haussmann's boulevards incorporate these calculations with mathematical perfection, achieving traffic flow optimization that modern engineers struggle to replicate even with advanced computer modeling, sophisticated traffic analysis software, and decades of research into transportation psychology and urban dynamics. The geometric relationships embedded in these intersections demonstrate understanding of human movement patterns, crowd behavior under various conditions, and optimization principles that required computational analysis not available until the advent of electronic computers. The precision with which these principles were applied suggests not trial and error experimentation conducted over decades of gradual improvement, but complete understanding of complex mathematical relationships that operated beyond the boundaries of 19th-century knowledge, understanding that encompassed not just engineering and mathematics, but psychology, sociology, and predictive modeling that anticipated technological and social developments that wouldn't occur for generations. Consider the logistics of executing such measurements across the varied terrains of different continents. Terrains that presented unique topographical challenges that should have necessitated completely different approaches, different mathematical solutions, different construction techniques adapted to local conditions that varied dramatically in ways that should have made identical implementation impossible. Each location presented geographical obstacles that had never been overcome at such scale. Environmental conditions that demanded innovations in engineering and construction that should have resulted in unique local solutions rather than identical global implementations. Paris sits on relatively flat terrain, carved by the gentle curves of the Seine River, where limestone bedrock provides stable foundation conditions that allow for consistent construction techniques, where temperate climate permits year-round building activities with relatively predictable weather patterns, where centuries of urban development had created infrastructure that could support major construction projects. Yet, even in this ideal environment, implementing such precision across varied elevations that rise and fall throughout the city, across soil compositions that change from limestone bedrock to river sediment, across underground infrastructure that included ancient Roman foundations, medieval sewers, and existing utility systems, should have required constant adjustment and recalculation that would have compromised the geometric precision observed. The Seine River Valley presents geological complexity that includes ancient alluvial deposits, limestone formations of varying hardness, underground water systems that affect foundation stability, and soil compositions that change significantly across relatively short distances. Implementing identical geometric specifications across such varied geological conditions should have required different foundation techniques, different construction methods, different materials adapted to local soil chemistry and groundwater conditions. Yet the geometric template was imposed with mechanical uniformity that ignored these geological variations, suggesting either construction techniques far more advanced than anything documented in 19th-century engineering, or coordination by intelligence that possessed complete understanding of geological science decades ahead of its time. St. Petersburg was built across marshland and islands where the Neva River meets the Baltic Sea, creating foundation conditions that represent one of the most challenging construction environments on Earth. The city floats on wooden pilings driven into unstable soil that shifts with seasonal freeze-thaw cycles that can move foundations several centimeters in a single winter, where permafrost conditions during Arctic winters are followed by spring floods that can undermine construction that wasn't designed to accommodate such extreme environmental variations. The marshy delta where St. Petersburg stands contains layers of organic matter, clay deposits, and sandy soils that provide inconsistent support for heavy construction, requiring foundation techniques that must account for seasonal ground movement, flooding conditions that can last for months, and soil chemistry that varies significantly across the construction area. Building on such terrain typically requires foundation systems specifically designed for local conditions, construction techniques adapted to seasonal weather patterns, materials selected to withstand extreme temperature variations, and moisture levels that would destroy conventional construction materials. Yet St. Petersburg achieves the same mathematical precision observed in Paris, implementing identical geometric specifications, despite foundation conditions that should have required completely different approaches, despite climate conditions that ranged from Arctic winters, where temperatures could freeze metal tools and make stone cutting impossible, to brief summers, where marshy conditions made heavy construction extremely difficult. Russian architects and construction crews somehow achieved geometric precision identical to their European counterparts, while working under environmental conditions that should have made such precision impossible, using the construction techniques and materials officially available in the 19th century. Buenos Aires sprawls across the Rio de la Plata Delta, where river sediment creates constantly shifting ground conditions that change with every flood, every seasonal weather pattern, every tidal variation that affects the massive river system that drains much of South America. The terrain changes with every flood season, every drought cycle, every major storm system that deposits new layers of sediment or erodes existing soil formations, creating construction challenges that should have required techniques specifically adapted to these constantly changing conditions. The Rio de la Plata Delta presents unique engineering challenges that include soil compositions that vary from sandy deposits to clay formations, groundwater levels that fluctuate seasonally, flood conditions that can inundate construction sites for months at a time, and soil chemistry affected by both freshwater river systems and saltwater intrusion from the South Atlantic. Construction in such environments typically requires specialized foundation techniques, drainage systems designed for local flood patterns, materials selected to withstand both moisture and salinity that would corrode conventional building materials. The soil composition in the Buenos Aires construction area couldn't support the massive stone structures built upon it using conventional 19th century construction techniques, which relied on direct foundation placement that required stable soil conditions and consistent load-bearing capacity. The building should have sunk into the marshy delta soil, shifted due to seasonal ground movement, or cracked due to differential settlement that occurs when heavy structures are built on inconsistent soil formations. Instead, they maintain their mathematical perfection across more than a century, demonstrating foundation engineering that exceeds documented capabilities of the 19th century. Washington, D.C. was designed around hills and the Potomac River, its avenues carved through varied elevations that required extensive grading and fill operations to create level surfaces for construction, through terrain that rises and falls dramatically across the city's footprint, creating engineering challenges that should have made identical implementation of geometric specifications impossible without major modifications to accommodate local topographical conditions. The Potomac River Valley presents complex topography that includes rocky outcroppings of different geological formations. River valleys that required extensive earthwork to create level construction areas, hills that needed to be graded or removed entirely to accommodate boulevard construction, and soil conditions that varied from solid rock to river sediment across relatively short distances. Implementing identical geometric specifications across such varied topography should have required extensive surveying to map elevation changes, complex engineering calculations to design grading operations, specialized construction techniques adapted to different soil and rock formations encountered throughout the construction area. Yet, the mathematical template was imposed with the same precision achieved on stable European foundations, implementing identical geometric relationships despite topographical challenges that should have required significant modifications to accommodate local conditions. Despite engineering obstacles that should have resulted in unique American solutions rather than specifications identical to those being implemented simultaneously in Paris, St. Petersburg, and Buenos Aires. Instead of adaptation that would reflect intelligent response to local conditions, we find imposition that treated radically different landscapes as if terrain itself was irrelevant to the design, as if gravity, geology, and geography were merely minor obstacles to be overcome by superior intelligence and technology that operated according to principles beyond 19th century engineering, technology that could impose identical geometric specifications regardless of local conditions, regardless of the geological and environmental challenges that should have made such uniformity impossible to achieve. The building heights present an even stranger consistency, a consistency that transforms architectural curiosity into mathematical impossibility, a uniformity that defies every principle of independent cultural development and suggests coordination operating beyond the constraints of documented 19th century communication and organizational capability. This consistency extends beyond mere numerical agreement to encompass proportional relationships, aesthetic harmony, and functional optimization that required understanding of human psychology, architectural theory, and urban planning principles that wouldn't be formally developed until the 20th century. The 22.5-meter standard appears not only in the grand boulevards of Paris, but in the major avenues of cities that had no documented architectural exchange with France. No recorded correspondence between architects working thousands of miles apart, no shared training programs that could have transmitted such specific technical knowledge, no cultural exchange mechanisms that could explain such precise uniformity across continents separated by months of difficult travel and communication barriers that made coordination extremely difficult. This uniformity encompasses not just building height, but facade proportions, window spacing, architectural detailing, and structural systems that required understanding of material science, construction engineering, and aesthetic theory that should have developed differently in different cultural contexts, different climatic conditions, different available materials, and different architectural traditions that had evolved over centuries to address local environmental and cultural conditions. St. Petersburg's Nevsky Prospect stretches through the heart of Imperial Russia, where golden domes of Orthodox churches pierce the winter sky above buildings that stand in military formation, each facade rising to the same impossible height despite being constructed in a climate that demands thick walls for insulation against Arctic winters, steep roofs to shed heavy snow loads, specialized foundation systems to accommodate freeze-thaw cycles, and building techniques adapted to working conditions where temperatures could make construction impossible for months at a time. Russian architects working in environmental conditions that required completely different approaches to heating, ventilation, structural design, and material selection somehow achieved the same proportional relationships as their Mediterranean counterparts, who were working in temperate climates with completely different environmental challenges, different available materials, different cultural aesthetic traditions, and different technical training that had developed over centuries to address local conditions. The Russian implementation required adaptation to Orthodox architectural traditions that emphasized different proportional relationships, different decorative elements, different spatial concepts than those found in Western European architecture, yet achieved facade proportions that matched French specifications with mathematical precision, suggesting either remarkable convergence of aesthetic theory or coordination by intelligence that possessed complete understanding of architectural harmony principles that transcended cultural boundaries. Buenos Aires' Avenida de Mayo cuts through the heart of South America's most important port city, where buildings were constructed with local materials quarried from regional stone formations, adapted to tropical climate conditions that required different ventilation systems, different structural approaches to accommodate seasonal weather patterns, different foundation techniques to address soil conditions unique to the Rio de la Plata Delta, designed by architects trained in Spanish colonial tradition that emphasized different proportional relationships, different aesthetic principles, different spatial concepts than those found in Northern European architecture. Yet, every building along the Avenida de Mayo rises to the same height achieved thousands of miles away, in completely different cultural and environmental contexts, implementing facade proportions that match European specifications despite being designed according to Spanish colonial architectural traditions. Built with local materials that had different structural properties, constructed in climatic conditions that required different approaches to building design, and executed by craftsmen trained according to different technical traditions that had developed over centuries in isolation from European influence. The construction techniques employed in Buenos Aires varied significantly from those used in Paris or St. Petersburg, utilizing different types of stone quarried from different geological formations, different mortar compositions adapted to local materials and climate conditions, different labor traditions that had developed according to Spanish colonial practices, different tools and equipment that were available in South American markets. Yet the final measurements match European specifications with a precision that suggests either impossible coincidence or coordinated implementation by intelligence that operated beyond regional limitations, beyond cultural boundaries, beyond the technological and organizational constraints that should have made such uniformity impossible to achieve. Washington's Pennsylvania Avenue connects the seats of American political power through the capital of a nation that was developing its own architectural traditions independent of European influence, where American architects were working with different materials and different aesthetic traditions that reflected democratic ideals rather than imperial grandeur, different construction techniques that had evolved to address North American environmental conditions, different proportional concepts that emphasized practicality and efficiency rather than the ceremonial grandeur associated with European capitals. American architects, working within the constraints of Republican architectural theory that emphasized simplicity, functionality, and democratic accessibility rather than imperial magnificence, somehow arrived at identical mathematical solutions that matched European specifications, achieving building heights that corresponded precisely with monarchical boulevard systems, despite working within political and cultural contexts that should have produced completely different architectural approaches. The American implementation required integration with existing urban infrastructure that had developed according to different planning principles, adaptation to democratic political concepts that emphasized public accessibility rather than aristocratic exclusivity, construction techniques that utilized locally available materials and American manufacturing capabilities, and aesthetic theories that were developing independently of European influence. Yet, American construction crews achieved geometric precision identical to their European counterparts while working under political, cultural, and technical conditions that should have produced uniquely American solutions rather than specifications identical to those being implemented simultaneously across multiple continents. This uniformity cannot be explained by coincidence, which would require probability calculations that approach mathematical impossibility when applied to the level of precision observed across multiple continents, by shared aesthetic preferences that could not have been transmitted across vast distances using available communication technology, or by the gradual diffusion of architectural ideas that would have required decades or centuries to spread across continents, and would have resulted in local variations rather than mechanical uniformity. The probability calculations for such convergence approach mathematical zero when we consider the number of variables involved, the precision of the measurements achieved, the synchronization of construction timelines, the coordination of materials and workforce management, and the complexity of implementing identical specifications across radically different environmental, cultural, and political contexts. We are observing coordination that should have been impossible given the technological and communication constraints of the period. Coordination that suggests intelligence operating beyond documented human capabilities, intelligence that possessed understanding of architectural harmony, urban planning theory, and construction engineering that exceeded anything officially available in the 19th century. The angular geometry of these cities reveals mathematical relationships that become more mysterious the deeper we examine them. Relationships that require computational capabilities that wouldn't exist for another century. The boulevards of Paris intersect at angles calculated according to what modern traffic engineers call optimal flow dynamics. These principles were not formalized until the 1960s, when computer modeling allowed urban planners to calculate the precise angles needed to minimize congestion while maximizing pedestrian and vehicle movement. The calculations require processing thousands of variables simultaneously. Pedestrian psychology, vehicle turning radii, weather effects on movement patterns, crowd density dynamics under stress conditions. This level of analysis demands computational power that exceeded anything available until the advent of electronic computers. Yet Haussmann's boulevards incorporate these calculations with mathematical perfection, as if their designers possessed computational capabilities that would not exist for another century. The 12-spoke radial design, emanating from the Arc de Triomphe, achieves flow optimization that modern traffic engineers struggle to replicate. Each angle calculated to channel human movement with maximum efficiency, each intersection designed to minimize conflict between crossing paths. The mathematics involved require understanding of human psychology, physics of motion, and probability theory that wasn't formally developed until the 20th century. More unsettling still, the same angular relationships appear in the redesigned sectors of every major city, modified during this period. The 12-spoke radial design, emanating from the Arc de Triomphe in Paris, mirrors the radial patterns extending from the Capitol building in Washington, D.C., and the Winter Palace in St. Petersburg. These are not approximate similarities. They are mathematical duplicates, with spoke angles matching to fractions of degrees across continents. The precision suggests either shared templates that no historical record documents, or coordination by intelligence that possessed measurement capabilities far beyond human limitation. And when we map these angular relationships on a global scale, another pattern emerges that defies conventional explanation entirely. A pattern that suggests these cities were designed not just for human habitation, but as components in a larger geometric system that spans the globe. When we map these angular relationships on a global scale, another pattern emerges that defies conventional explanation, a pattern that transforms urban planning into something approaching cosmic architecture. The major avenues of these redesigned cities align not only with local geographic features, but with astronomical coordinates. The primary boulevards of Paris align with solstice and equinox solar angles, calculated to a precision that requires understanding of celestial mechanics decades ahead of its time. The radial design of Washington, D.C. corresponds to planetary orbital relationships that weren't accurately calculated until the development of modern astronomy. The angles between the major avenues mirror the orbital positions of Mars, Jupiter, and Saturn with mathematical precision that demands telescopic observations far more sophisticated than anything officially available in the 1850s. These instruments could barely determine planetary positions to the nearest degree, yet the geometric relationships embedded in these cities require calculations accurate to minutes of arc precision that wouldn't become available until the advent of photographic astronomy and electronic computation. The grid modifications in St. Petersburg mirror lunar phase calculations that incorporate the complex gravitational interactions between Earth, Moon, and Sun. The mathematics involved require understanding of three-body orbital mechanics that wouldn't be solved until the space age. Either the urban planners of the 1850s possessed an unprecedented knowledge of astronomical mathematics that history has failed to record, or they were following templates created by intelligence that understood celestial mechanics at a level we've only recently achieved. Computer analysis reveals that these alignments account for precession of the equinoxes, variations in Earth's orbital eccentricity, and subtle gravitational perturbations that affect celestial coordinates over centuries. The designers planned not just for their own era, but for astronomical changes that wouldn't become apparent for generations. This level of astronomical sophistication suggests either time-traveling architects with access to future knowledge, or coordination by intelligence that possessed observational and computational capabilities that exceeded anything officially developed until the late 20th century. We are not looking at urban planning. We are looking at a global coordinate system embedded in terrestrial architecture. A system that connects earthly geometry with celestial mechanics in ways that suggest purpose beyond human habitation. Purpose that may extend far beyond our understanding of what cities are meant to accomplish. The construction timelines present their own impossibility, an impossibility that becomes more staggering the more closely we examine the human and material resources required. Haussmann's renovation of Paris officially began in 1853 and was substantially completed by 1870. 17 years to transform a medieval city into a geometric masterpiece. But the numbers tell a story of impossibility, masked by historical acceptance. During this 17-year period, approximately 95 kilometers of new boulevards were carved through existing urban fabric. This required the demolition of thousands of medieval structures, some standing for centuries, their foundations grown deep into Parisian soil. The excavation alone demanded the removal of millions of cubic meters of stone and earth. Each cubic meter weighed approximately 2 tons. We're talking about moving mountains of material, using horse carts, hand shovels, and human muscle power. Modern earth-moving equipment can process perhaps 1,000 cubic meters per day under ideal conditions. Using 1850s technology, a team of 50 workers might move 50 cubic meters in a day of back-breaking labor. The scale differential is almost incomprehensible. The construction of uniform buildings along the entire length of the new avenues required millions of precisely cut stone blocks. Each block had to be quarried, shaped, transported, and positioned with mathematical accuracy. Using period tools, master stonemasons could produce perhaps 3 finished blocks per week. Even with unlimited resources and manpower, such a project should have required several decades of continuous labor. Yet the timeline suggests construction rates that exceed modern capability, achieved using technology that was demonstrably inadequate for the task. Yet, similar transformations occurred simultaneously in other cities, with even more compressed timelines. The major avenue reconstructions in Buenos Aires were completed in just 12 years, despite the additional challenges of importing materials and expertise across an ocean. St. Petersburg's boulevard system was finished in 14 years, accomplished despite subarctic conditions that limited construction to 6 months per year. Washington, D.C.'s modifications took 10 years, achieved while the nation teetered on the brink of civil war. These are not merely impressive engineering achievements. They represent logistical accomplishments that strain credibility when examined against the technological capabilities of the era. Either the official timelines are fabrications, or these projects utilized methods and resources that operated far beyond the documented capabilities of the 1850s. The labor requirements alone present a mathematical paradox that becomes more disturbing the deeper we investigate. Conservative estimates suggest that Haussmann's renovation required a continuous workforce of at least 30,000 skilled laborers, architects, engineers, and supervisors working every day for 17 years. This figure represents nearly 1% of Paris's total population, dedicated exclusively to urban reconstruction. 1 in every 100 Parisians, men, women, children, elderly, infirm, would have needed to work full-time on construction sites for nearly 2 decades. But this calculation assumes that every required worker was locally available and properly trained. In reality, the skills demanded minor precision stoneworking, advanced surveying, mathematical calculation, architectural drafting, were rare specialties possessed by perhaps 1 in 1,000 individuals. A master stonemason required 7 years of apprenticeship to achieve competency, another decade to develop the precision demanded by these projects. The guild system of the era protected such knowledge jealously, limiting the number of qualified practitioners. Similar projects occurring simultaneously in other major cities would have required hundreds of thousands of workers globally, all possessed of identical skills, all working according to identical specifications, all completing their tasks within an impossibly narrow time frame. The global demand for specialized labor during this period exceeds the entire trained workforce of Europe and America combined. Either these projects recruited workers from sources that left no historical trace, or they employed methods that required far fewer human hands than conventional construction. Contemporary accounts of these reconstructions describe construction activities that proceeded with machine-like precision. Workers appeared to follow standardized procedures that had never been publicly documented. Building techniques emerged that were more efficient than traditional methods, yet were never formally taught or recorded in architectural manuals. Employment records from the period show sudden increases in skilled construction workers in every affected city. These workers appeared as if from nowhere, possessed skills that had not been formally taught anywhere, completed their tasks with efficiency that exceeded normal human productivity. and then vanished from historical record without explanation. No records of where they came from, where they went, how they acquired their extraordinary capabilities, or who coordinated their simultaneous deployment across continents. Modern industrial analysis suggests that even with optimal organization and unlimited resources, the described construction rates demand productivity levels that exceed human physical limitations by factors of 10 or more. Either these workers possessed capabilities far beyond normal human performance, or they had access to tools and methods that operated according to principles we cannot identify from historical records. The workforce that executed these projects left traces that become more puzzling the more closely we examine them. They achieved the impossible, worked with supernatural efficiency, and then vanished as mysteriously as they appeared, leaving behind only the geometric perfection of their impossible accomplishments. The financial aspects of these simultaneous global projects reveal another layer of impossibility that challenges every principle of 19th century economics. Haussmann's renovation cost approximately 2.5 billion francs, equivalent to nearly the entire annual budget of France. This figure represents not just municipal expenditure, but national financial commitment that should have bankrupted the French treasury. Similar expenditures occurring simultaneously in other countries should have created detectable international financial flows, massive loan agreements, or economic disruptions visible in contemporary financial records. The movement of such capital across continents would have reshaped global banking. Yet contemporary financial records show no evidence of the massive capital movements that such coordinated global construction would have required. No international banking syndicate capable of such coordination existed. No financial instruments sophisticated enough to manage multi-continental investment had been developed. The banking systems of the 1850s operated on personal relationships and regional connections. International finance was limited to trade transactions and government bonds. The sophisticated investment mechanisms required for synchronized global construction simply did not exist. The source of funding for these projects remains as mysterious as their coordination. Official histories attribute financing to government bonds, international loans, and public-private partnerships, but mathematical analysis reveals that these sources could not have provided the capital required. Government bonds of the era rarely exceeded a few million francs. Even the largest international loans negotiated during this period were measured in tens of millions. The scale of expenditure for these projects required financial resources that exceeded the combined wealth of most European treasuries. Insurance records reveal another anomaly. Projects of this scale should have required comprehensive insurance against loss, damage, theft, and failure. Yet no such policies exist in contemporary records. Either the projects proceeded without financial protection, impossible for such massive investments, or they were protected by guarantees that operated outside conventional financial systems. The financial mechanisms required to support simultaneous mega-projects across multiple continents would have necessitated banking and investment systems far more sophisticated than any that existed in the 18th systems that could coordinate global capital flows, manage currency exchange across multiple markets, and synchronize investment timing with precision that demanded instant communication. Exchange rate fluctuations alone should have made such coordination impossible. The franc, the pound, the ruble, the peso all operated as independent currencies with values that changed daily based on political and economic conditions. Synchronizing massive expenditures across these different monetary systems required financial sophistication that wouldn't develop until the late 20th century. Modern economic analysis reveals that the claimed financing methods could not have provided even 10% of the capital required. The mathematical gap between documented financial resources and actual expenditures exceeds any reasonable margin of error. Either the official cost estimates are fabrications, or these projects were financed through mechanisms that operated entirely outside the documented financial systems of the era. Mechanisms that could mobilize vast wealth without leaving traces in contemporary banking records. We are looking at evidence of financial capability that transcended every known limitation of 19th century economics. Either these projects had access to wealth that operated beyond conventional monetary systems, or they were financed by intelligence that possessed resources far beyond anything officially documented in human history. When we examine the architectural drawings and planning documents that survive from this period, we encounter another anomaly that challenges conventional understanding of 19th century technical capability. The blueprints for these projects display a level of technical sophistication that surpasses anything produced before or since. These are not the work of human hands guided by primitive instruments. They represent precision that demands explanation. The drawings incorporate engineering calculations that were not formally developed until the 20th century. Stress analyses that account for wind loads, seismic forces, temperature variations, and material fatigue over centuries of use. These calculations require knowledge of material science and structural physics that wouldn't become available for decades. Modern engineering software confirms that these 19th century calculations achieve results that match current building codes with frightening precision. Either the architects of this period possessed supernatural understanding of structural mechanics, or they had access to computational methods that transcended human capability. The drafting itself reveals precision that exceeds human capability. Lines are drawn with tolerances measured in fractions of millimeters. Geometric constructions achieve mathematical perfection that would challenge modern computer-aided design systems. Measurements are calculated to degrees of accuracy that demand tools and techniques unavailable in the 1850s. Either the architects of this period possessed supernatural precision in their manual drafting, or they had access to technology that history has forgotten to record. The consistency of these drawings across different cities presents its own puzzle. Blueprints for modifications in Paris match the technical specifications found in planning documents from St. Petersburg, Buenos Aires, and Washington, D.C. Not only do the measurements align, but the drafting techniques, the calculation methods, and even the symbolic notations used in the margins show identical characteristics. It is as if all these projects were designed by the same individual or team, working from the same technical standards, using the same tools and methodologies. The materials used in these constructions display properties that challenge our understanding of 19th century technology. Stone blocks cut for the new boulevards show precision that rivals modern laser cutting. The uniformity of dimensions across thousands of building facades suggests manufacturing capabilities that should not have existed. The cutting marks on these stones reveal tool characteristics that don't match any known 19th century technology. The surface finish achieves smoothness typically associated with industrial diamond cutting. Yet, these cuts were allegedly made with hand tools and primitive machinery. The mortar compositions used to bind these structures demonstrate chemical knowledge that was not formally documented until the development of modern cement science. Chemical analysis reveals proprietary additives and binding agents that shouldn't have been available or understood in the 1850s. Some samples contain trace elements that suggest high-temperature processing techniques requiring industrial furnaces that didn't exist in the documented technology of the era. The chemistry involved exceeds what traditional lime mortar could achieve, yet historical records show no evidence of the advanced kilns and chemical processes required. Most mysteriously, the stone itself appears to have been sourced from quarries that cannot be identified. The limestone used in Haussmann's boulevards does not match any known quarry in France. Geological analysis reveals mineral compositions that don't correspond to any documented stone sources. Similar unexplained stone sources appear in every major city, modified during this period. Either these projects required the development of entirely new quarrying operations that left no historical trace, or they utilized materials from sources that remained deliberately hidden. The transportation of these materials presents logistical challenges that multiply the impossibility. Moving millions of tons of precisely cut stone from unidentified quarries to multiple city centers across continents would have required transportation networks far more extensive than any that existed in the 1850s. The rail systems of the period could not have supported such massive cargo flows. Shipping networks lacked the capacity for simultaneous delivery to multiple international destinations. Yet the materials appeared exactly when needed, in precisely the quantities required, as if summoned by mechanisms that operated beyond conventional logistics. We are looking at evidence of supply chains that operated according to principles we cannot identify. Materials appeared without documented sources, moved without adequate transportation, and arrived with precision that suggests coordination far beyond the capabilities officially available in the 8th. The workforce that executed these projects left traces that become more puzzling the more closely we examine them. Traces that point toward coordination mechanisms operating far beyond conventional human organization. Employment records from the period show sudden increases in skilled construction workers in every affected city. These workers appeared as if from nowhere, possessed skills that had not been formally taught anywhere, completed their tasks with efficiency that exceeded normal human productivity, and then vanished from historical record without explanation. Contemporary observers noted that these workers operated according to techniques that were unfamiliar to local craftsmen. They used tools that were not available in local markets. They followed procedures that had never been documented in trade manuals. Their efficiency suggested training that was far more advanced than anything provided by traditional apprenticeship systems. Yet no records exist of where this training occurred or who provided it. The workers appeared with complete skill sets that typically required decades to develop. The coordination of activities across these global construction sites suggests communication capabilities that transcended the limitations of 19th century technology. Telegraph systems of the period were limited to major routes and were frequently unreliable. International message transmission took weeks or months. Yet the synchronization observed in these projects indicates real-time coordination that should have been impossible. Modifications to original urban plans occurred simultaneously across continents, as if directed by a central authority with immediate global communication capability. Design changes implemented in Paris appeared in other cities within days rather than the weeks or months that conventional message transmission would have required. This simultaneity suggests either the presence of communication technology far in advance of anything officially recognized, or coordination by intelligence that operated through means we cannot identify. The mathematical principles underlying these urban designs reveal knowledge that was not formally available in the 1850s. Traffic flow optimization, angular geometry for maximum efficiency, building height calculations for optimal light distribution, boulevard width specifications for crowd control. All incorporate advanced mathematical modeling that would not be developed until the 20th century. The precision with which these principles were applied suggests not trial and error experimentation, but complete understanding of complex mathematical relationships. Understanding that required computational capabilities beyond anything officially available in the 1850s. When we analyze the geometric patterns using modern computational methods, we discover that the city designs incorporate mathematical constants that were not recognized until decades after their implementation. The golden ratio appears consistently in the proportional relationships between boulevard widths and building heights. Fibonacci sequences emerge in the spacing of major intersections. Fractal patterns repeat in the smaller street networks that branch from the main avenues. The integration of these mathematical principles into practical urban design required computational capabilities that exceeded anything available in the 1850s. Calculating the optimal angles for traffic flow across multiple intersecting boulevards demands the processing power of modern computers. Yet these calculations were implemented flawlessly, using only the manual calculation methods supposedly available at the time. As our investigation deepens, the evidence points toward a conclusion that challenges everything we understand about the limitations of 19th century civilization. The mirror cities were not independent achievements of human ingenuity operating within the constraints of their era. They were coordinated implementations of a master design that transcended the technological, communicational, and organizational capabilities supposedly available at the time. The mathematical precision, the synchronized timing, the identical specifications, the astronomical alignments, the anticipatory planning, all point toward coordination by intelligence that possessed capabilities far in advance of anything officially recognized in the 1850s. Whether this intelligence was human or something else, whether it operated through hidden technology or through mechanisms we cannot identify, remains the ultimate question that the evidence cannot yet answer. What we can conclude with mathematical certainty is that the official explanation for these urban transformations is statistically impossible. The convergence of so many identical elements across such vast distances within such compressed timeframes cannot be explained by coincidence, independent development, or gradual cultural diffusion. Something else was operating during those crucial decades, something that possessed global reach, advanced planning capability, and technological resources that history has either forgotten or never officially acknowledged. The mirror cities stand as monuments to this hidden intelligence. Every boulevard that stretches in perfect geometric harmony, every building that rises to mathematically calculated heights, every intersection that channels traffic with optimal efficiency serves as evidence of planning that transcended the limitations of its supposed era. We walk through these urban environments daily, surrounded by proof of capabilities that officially did not exist, following routes designed by intelligence that history cannot explain. The investigation continues because the questions have no conventional answers. Who designed the master plan that shaped the world's greatest cities? What technology allowed its synchronized implementation across continents? What intelligence possessed the mathematical knowledge, the astronomical understanding, and the predictive capability to create urban environments that continue to function optimally more than a century after their completion? The mirror cities reflect more than light. They reflect the presence of something extraordinary operating within our historical record, something that challenges every assumption we hold about the capabilities and limitations of our ancestors, something that suggests human civilization has been shaped by influences that remain hidden behind the geometric precision of the streets beneath our feet. The truth lies hidden in plain sight, written in the language of mathematics across the urban landscapes we inhabit daily. The mirror cities are more than architectural achievements. They are messages from intelligence that possessed capabilities we are only beginning to suspect. Until we can decipher these messages, until we can explain their impossible precision and synchronized implementation, we will continue to walk through evidence of hidden history, surrounded by proof of capabilities that officially never existed. The investigation must continue. The questions demand answers. The mirror cities reflect truths that cannot be ignored forever.